Let's talk about Hooke's law. I found there's a story behind Hooke's law that he had thought he had figured out this relationship, this rather cute relationship, and so he basically translated the essence of it into Latin, scrambled the letters around, and had that published. And which I always thought was odd, that eventually someone clued me in, as it was sort of like establishing a copyright early on, that you do this so that later on if someone else says they discovered it, you can go, oh, wait a second, if you look at this Latin anagram, I figured it out first. So it's the fact that the force that an object applies is directly proportional to how far it gets displaced. So if we take the ordinary slinky, if I pull down on the slinky is pulling up on my hand. That the force that the slinky exerts on, in essence, the last coil, is directly proportional to how far I stretch it. The more I stretch it, the more force is applied. And it also works in an ideal case of, if I push it up, it's also exerting a force proportional to, a force downwards proportional to how much I am displacing it. The negative sign is basically indicating the force is opposite the direction of displacement. So if I stretch it, the force is trying to pull it back towards the middle or towards equilibrium. If I compress it, the force is trying to push it away, push back towards equilibrium. So I can find this spring constant in a very simple way. And unfortunately, I put stuff away. How dare I do that? So I can find the spring constant because if I know a particular mass, so I have a coil right here, I can, this little red flag right here, like red marker, I can put a meter stick next to it. This red marker can tell me exactly where that is. I can apply a mass to it. This marker will move to a new spot. And so if I take a coil or something of that nature and it just sort of hangs there, and then I add a mass to it, and it's in a new equilibrium position, well, if I do my force diagram, I have mg acting down, the weight, and then acting up, let's put in W, G equals mg. Acting up, I have the force from the spring, which is going to be the spring constant times how far it displaced. Now the negative sign is telling me the direction that is opposite the displacement. I know I pulled it down, so I know that force is up. I don't have to add the negative sign again. Where this distance here would be delta x. Just a quick and dirty example here. I have a spring. I apply a mass of 5 kilograms to it and put it in a new equilibrium position, and so the spring stretched, we'll just say 3 meters. What is the spring constant? Let's put this on Earth 2. And so I have mg is equal to k delta x. $30 is equal to k times 3. K is 10. And then I will toss out to you, what should the units be?
So we're figuring out the spring constant?
Yes.
So is it an energy unit?
Not by itself. Typically people don't bring the energy unit into it, but I could force it if I had to.
Does it have units because it's a constant?
Yes, it does have units.
spring units.
What did I divide? How did I get 10?
Meters per second.
How did I get 10?
You divide by meters.
Okay. What did I divide by meters?
Kilogram per meter. Kilogram meters per second. The mg.
What are the units of mg?
Newton.
Oh, pardon?
Newton.
Yeah.
Newtons per meter.
Yeah, newtons per meter. All right. So what this claims is that for this particular spring, it would take 10 newtons to stretch it 1 meter. It takes 20 newtons to stretch it 2 meters. It takes 30 newtons to stretch it 3 meters. There's a pattern here. So if I took this same spring and then put it horizontally on a frictionless plane, because physicists like to do that, well, we know one person who has an alibi for this moment.
Blessed assurance.
Until I lose the video, unless you come up with it. So we have so if I put it on a horizontal frictionless surface, then I can stretch it out, let go, and it would actually end up oscillating back and forth if I let go. Now this is not ideal, so it's not going to do it forever, but similar to if I take this, I pull it down, it will oscillate up and down in a particular pattern. Questions before we talk about what that pattern is? And let's talk about what that pattern is. So I take that spring, I attach a mass to it, and this will be its equilibrium position right here. I then take it. It's an ideal spring. Part of an ideal spring is, one, it doesn't have any dampening effects. There's no friction. It will not interfere with itself. I mean, obviously, a slinky will interfere with itself. There's only so far it can compress it. But in an ideal spring, it will not. Frictionless surface down here, so I pull it out, I stretch it out to a certain length, and then I let go. So I stretch it out this far. We will call this A for amplitude. Now I know that F equals ma. At least that's what I've been telling you. And the net force acting on it is the force from the spring. So this is an elastic force. Now I use an S for elastic because the subscript E I'm saving for 152 when I use it for electric. So I'm using S for elastic or for spring. I know that spring force is equal to mass times the acceleration of this object. Let's assume that to the right is positive. Well, that makes a huge amount of difference. But this becomes negative K delta X is equal to mass times acceleration. Assuming, of course, this obeys Hooke's law. Well, if we think about that, if I just go ahead and I'm going to simplify it, it does work. And if there's a video out there where I go through a more detailed example, I'm just going to go ahead and set X is equal to 0 here, just to make life simpler. So this now becomes negative K X is equal to mass times acceleration. Now, if we think about it, I know that acceleration is the change in velocity over the change in time. And I know that velocity is the change in position over the change in time. So acceleration is the change with respect to time of the change in velocity. Oops, sorry, wrong one. position with respect to time. Or, written in slightly more formal language, delta squared x over delta t squared. The notation might seem a little bit awkward. If you've had calculus, then you know where I'm going with this. It's just a second derivative. If you haven't had calculus, this is the math notation for, you're taking the change in x with respect to time, and then you're taking that change with that with respect to time. In other words, the slope of a slope. And you've all been through those exercises and presumably remember it all incredibly well. So if I have a parabola here, let's say this is x first time, then if I look at the slope starts out small and gets bigger and bigger. My slope here is constant, so my acceleration first time would be a straight line. So if this is a parabola, if x is a parabola, acceleration is a horizontal line. So I need some function to describe x, to model the motion of this harmonic motion. I need some function so that when I do the slope of the slope, I end up with the negative of itself. Because acceleration is the slope of x. I got a negative sign here, so I need some function so that when I do the slope of the slope, I basically get the negative of what I started with. M and K we'll worry about later. Well, this obviously won't do this. This is not the negative of that. But there is a function, which is the negative, which when I do the slope of the slope, I end up with a negative of itself. And that is?
So,
Absolutely.
more specific.
Now, I'll give a little hint here. We have an object that's going to oscillate back and forth. Or let's just do it vertically, just because it might be more natural. Is it's oscillating back and forth over time, so if I did it over time,
Sine function?
or a cosine function, whichever one. Well, let's see if that actually holds true, or I'm just sort of making stuff up
As you do.
this time. Did you say as you do?
Yes.
Yeah. I'll buy that. So if I have a sine function, poorly drawn, if that's x first time, the slope of it, well, I know the slope. What's the slope here?
0? Or is it that they're referencing the top?
I missed the last thing you said.
Is it just the top part, or is it
Just the very tip.
0?
It's 0. And the slope here,
Also, yeah, 0.
and in between, positive or negative.
Negative?
Okay. And over here,
Positive?
and here,
Positive. Or negative? No, it's going up.
the slope is positive. So if this is a sine function, so if this is x is sine of t, this is, well, not everyone necessarily has gotten this in class, in math class, but for those who have, what is that graph of?
Cosine.
You were way out from left field on that one.
Way left. Cosine?
Cosine. And if I then did the slope of that, well, it starts out, that's supposed to be 0 there. It's 0 here, the slope is 0 here. The slope is negative, the slope is positive. And that looks like the upside down version of this. This is the negative, so acceleration is the negative sine of t. And matter of fact, the pattern is, I feel like I've written this on the board before, but you would go to sine to cosine, to negative sine, to negative cosine, you kept going, be back to sign again. It'll just cycle through those four.
Why is acceleration negative when the other two are positive?
Think about it in this case right here. I pull it out here, the displacement is positive. When I let go, it's going to accelerate in that direction,
Yeah, okay.
in the negative direction. Now this would be a case the velocity is also negative, but we started with cosine. We started with cosine on here. If I pull this out and let time is equal to 0 when I let go, it's at the amplitude.
Okay.
So the velocity would be negative, acceleration is negative. Is that sufficient?
Yeah.
Okay. All right, so now I have to worry about this K and M. Yes, I have to.
Now, if you don't mind me asking a previous question. We're setting these up as trig functions y.
All right, so based upon Newton's second law, and the fact that we're dealing with a spring that obeys Hooke's law, F equals ma, the only force the net force acting on this, not the only, but the net force is the spring force, which is negative k delta x. I simplified it and just made that negative kx is equal to mass times acceleration. The solution to this problem has to be some function so that since this is the slope of this, I need some function that when I get the slope of the slope, I end up with a negative of what I started with. So if this is cosine, this better be negative cosine.
Yeah.
Because mass is a positive number, k is a positive number.
Okay then. And then you did the a's and the x's here and there.
Yeah.
And there.
Yeah.
You keep saying springs that obey Hooke's law. Are there springs that don't?
Well, like the slinky, for example. You have to take into, the slinky has mass, it will interfere with itself. I can't compress it any farther
So
than it will go.
this applies to ideal springs?
It applies to ideal springs. Now it turns out that a slinky, there's one adjusting factor that you need to throw into it, in essence the effective mass of the slinky. Once you figure that out, then it works. You can come up with pretty accurate predictions. Now, if I did the sine of 2t, what does that 2 do?
To the graph or just in general?
Pardon?
To the graph or just in general?
To the graph.
It would increase the amount of, it would either increase the amount of maximums and minimums or stretch it out. I forget which one it is.
It's either a stretch or a shrink.
All right. So goes like, it takes that graph and does this or that.
Yeah.
Okay.
I think it does that.
Or
That.
there you go.
Okay.
Now your first answer of the possible answers was the second best choice.
Understood. Just, at least I didn't say it goes up.
Yes, thank you. So it does indeed stretch it. So imagine that, another way of looking at this is if I have a wheel that's rotating and I've got a little peg right there that rotates with it. As that peg rotates with it, if I'm just looking at the projection onto a vertical axis, it starts here, it goes up, it goes down, and then back to here again. That too doubles the angular speed of the wheel. If it's or a half, it would cut it in half. All right, so the graph now looks like, so it's going to end here. That was horrible because I ended in the wrong spot. It should end here. That's halfway point. So still is the same amplitude. So what does that do to the slope? If I take my plot like this and I cram it in like that, what does it do to my slope?
Makes it higher.
Yeah, matter of fact, it doubles it. If that's a 2, it doubles it. So my velocity is now going to be up here. And it also will be in half the time, so. So not only have I shrunk this, but I made it longer, my velocity, so my acceleration actually will be 4 times the slope. That's still 0 off the board. And the general rule is if I have some function, if x is equal to some amplitude times the sine of omega t, think of omega as angular speed of the wheel. In this context, it's called the angular frequency, but it has the exact same units as angular speed and the exact same symbol and
Angular.
yeah, angular frequency officially, but they look and taste the same. So if that's my position, my velocity is a omega cosine omega t. My acceleration is a omega squared cosine, negative a omega squared sine omega t. If you kept going, so the jerk would be negative a omega cubed cosine omega t. Snap would be a omega to the 4th sine omega t.
Snap. That's 152 stuff.
151. After jerk, there's snap, crackle, pop.
Ooh. Are we gonna be dabbling into snap, crackle, and pop?
That is between you and whoever buys groceries for you.
Understood.
So we had those equations before, the v equals cosine t. And then we had I guess just the same thing, but those are just adding numbers into it that could be a possibility for the graph.
Yes.